Okay? If you thought isn't absolutely a convergence automatically convergent, if you really go back to the definition doesn't say anything about convergence of this one. It only says about after you put the absolute value is a convergence, right? So now we're proving as a theorem that if it is absolutely convergent, without the absolute value is automatically convergent, which is this first one here is an example. Okay? Any confusion at this point? What the term is suggesting is not a proof. That's what I'm saying. So here's a proof. Why is it so? And I'm going to look at the partial sum, sk, of this thing, j going from 1 through k, aj. And I'm going to write down different partial sum, and I'm just going to explain in words. I hope that makes sense. It's pk minus nk. Bo, do you have a question? You have a very peculiar face you're making. Right. Let's do that. Sk is split as a pk. These are all positive terms. Sum of positive terms. Sum of positive terms. This all together with a negative sign. This is a sum of negative terms. Is this decomposition kind of make sense? It's a sum of k terms, so some of them will be positive and some of them will be negative, right? So I split it, and I pulled out the negative. Make sense? So what would you say about the sign of pk? Is the sign of pk is positive? How about nk? Is nk negative? I pulled out the negative there, right? So nk is still positive. I got the negative outside, so nk is also positive. But it's a group of terms coming from the negative terms. But it's put the absolute value around it. Okay? So the goal is that is to show pk and nk converges. Both converge. So this is a partial sum, right? If I can show pk and nk both converges, and then sk converges. It was a theorem. It's only two terms, right? So the limit distributes that. So how can I show that pk and nk both converges? What is the only condition we have about here? There's no condition. It's just very general description. The only condition we have is absolute convergence, right? It's absolute convergence. So absolute convergence is what we have. So let's see what that means. The partial sum going j from 1 to k of not aj, what is that? Absolute convergence. You put absolute value around it, right? This one is now, can you write this one? pk is a part of it. They're all positive. It's good, right? And what about nk? Nk were all negative, nk are negative, but we put absolute value to each term. That becomes a positive like that, right? Correct? So these are all positive terms. Positive terms. All right, make sense? Another thing, that, and this converges to number L. Why does this converge to L? What's that? Why does this pk plus nk converge to L? We assume it's absolutely convergent. So this sequence converges. This partial sum converges after you put the absolute value around. Does that make sense? We assume this converges. Good? Yes. Right. Absolute convergence. It means that this entire sequence converges. So pk plus nk converges. Absolute value of ak thing. That's right. Yeah. All right. This is the meaning of the absolute convergence. Is that good? How about this thing? Is the pk increasing or decreasing? pk increasing? How can you explain that pK is increasing? Why is that? Positive terms keep adding on, right? If you look at more and more terms, we're collecting more and more positive terms, right? How about NK? Yeah, NK is the positive part of the negative term. If you keep collecting it as we throw in more and more K, sometimes it's a stagnant, right? Sometimes there's no more negative terms kicks in. So we have to wait along, but maybe it stops right there. Maybe eventually more positive terms kicking in, right? So it's not strictly increasing, but it's increasing, right? At least it's non-decreasing. Is that the better way of describing? So maybe it's a better term. It's non-decreasing. It never decreases. You add it or don't add it. That's what's happening as you increase that. Does that make sense? Non-decreasing. So from there, I hope it's obvious that pK plus NK eventually goes to L by keeps increasing, right? So therefore, there's no chance that this is going to be greater than. If it is pK plus NK's one time is greater than L, it keeps on going. There's no way coming back to L, right? So this pK plus NK will never exceed L, correct? If it exceeds, pK just keeps going because it keeps increasing, and there's no chance that it's going to come back to L. Same for the whole thing, because it keeps increasing. Any question? Non-decreasing means it's never going back. Once you exceed L, there's no chance you can go back to L. Therefore, it must stay below L. Good? So here is where we use this monotone, bounded monotone sequence theorem. So did we show that pK is monotone, is non-decreasing, right? And pK is also bounded by L. Is that true? Because NK is positive. And NK is also bounded by L because pK is positive. Sum is less than L, and how can be one of the positive terms be greater than? It has to be less than. So both bounded, right? So what theorem are we using to conclude the convergence of pK and NK? Sabrina, can you close the door for us, please? It was a bounded monotone sequence theorem, right? If this pK sequence is bounded and is monotone, it must converge. We don't know which one, but it must converge. So pK converges to where? Let's say L1. And NK must converge to some L2 because of the bounded monotone sequence theorem. That was our goal. pK and NK both converges to one term, the different term. Then we can show limit sk, k approaches infinity of sk. This is how we show the infinite series approach. The what happened to the partial sum. This one is a limit. K approaching the infinity of this aj is now splitted like this limit k approaches infinity of pk minus nk, right? So we saw that pk and nk both converges because of the condition of absolute convergence. So this one is going to be L1 minus L2, right? So absolute series converges to L1 plus L2, but without absolute value it converges to L1 minus L2. And it's not easy to figure out what that L1 and L2 is in practice. But theoretically, then it converges. So does that prove that if it is absolutely convergent, then individual decomposition part converges because of the bounded sequence theorem? That makes the difference, which is the series without absolute value, must converge as well. So that's the proof. Make sense? Did that answer your question, Bo? Or still lingering there? What was your question? Just curious. You can ask later, if you don't want to. But this absolute convergence in your hand, then you have a convergence. If you don't, then don't try to conclude anything. There's no other theorem that guarantees anything in the opposite case. Absolute convergence implies something. It's very strong. Convergence doesn't imply absolute convergence. Make sense? All right. So let's Write that. Absolute convergent implies convergent. That's the content of this theorem. But if you have convergent, no other information, it is not sufficient information to conclude absolute convergent. I think that was the content of our discussion. Good.